Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome to the Investigator's Quest, the evolution of advanced RAG. Today, we embark on a journey deep into the digital archives, moving beyond the simple search engine into the realm of intelligent knowledge synthesis. Retrieval Augmented Generation, or RAG, has fundamentally changed how large language models interact with external knowledge, allowing them to provide timely, accurate, and grounded answers. But just like any technology, RAG is constantly evolving. We began with a simple tool, but the demands of modern data retrieval require something far more sophisticated, a system capable of true investigation. Over the next few minutes, we will trace this evolution, starting from the basic functions and moving toward complex, cognitive architectures. We will learn how to transform a naive lookup mechanism into a system that can brainstorm, reason across disparate facts, and remember previous interactions. This is the pursuit of the next level of knowledge, and you, the audience, are about to become the architects of this advanced intelligence. Let us begin our quest. Our story begins with the foundational model of RAG, which we call the Library Clerk. This is standard or naive RAG. Think of the Library Clerk as diligent, accurate, but utterly literal-minded. Its function is straightforward. When you ask a direct question, it assumes a simple one-to-one mapping exists between your query and a single supporting document in its archives. It excels at answering factual questions like, "What is the capital of France?" or "When was the company founded?" The process is a simple, linear pipeline, as shown here. First, we ingest the documents into a vector store. Second, based on the user's query, we retrieve the single best matching chunk of text. Third, we generate the answer using the retrieved text and the large language model. This system is efficient, fast, and works perfectly well, provided the knowledge needed is contained neatly within one, easily identifiable location. This simplicity is its strength, but also, as we will soon see, its primary vulnerability when faced with complex, real-world questions. But what happens when the user's query demands synthesis, comparison, or abstract reasoning? The Library Clerk system faces its first crisis, what we call the unanswerable question. Consider a complex, multifaceted query like. Compare the economic impact of the steam engine in 1850s London to the impact of the internet in 1990s Silicon Valley. There is no single book, no single document snippet, titled A Comparative Analysis of 19th Century Steam Power and 20th Century Internet Impact. The Library Clerk, trained only for the one-to-one mapping, freezes. Its retrieval mechanism fails because it cannot find an exact match for the synthesis required. It might retrieve a document about steam engines and a separate document about the internet, but it lacks the internal mechanism to realize both are needed and combine their insights effectively into a coherent answer. The linear path that defined naive RAG is fundamentally broken, leading to a zero result or a poor, ungrounded response. This failure forces us to upgrade our simple clerk into a true investigator. The first upgrade in our journey transforms the Library Clerk into an investigator. The investigator understands a crucial truth. Users are often terrible at prompting, and a single, narrowly defined query might miss the target entirely. Instead of trusting a single search term, the investigator's first power is to generate a prism of perspectives. This technique is called RAG fusion. RAG fusion addresses the zero-result problem by transforming one narrow query, such as "Why is the project broken?" into many potential leads. What were the known defects in the project's infrastructure? List the communication failures that occurred last week, or identify recent changes to the deployment pipeline. By brainstorming multiple variations of the query from different angles, we create a wide net retrieval strategy. If the original query fails to retrieve relevant documents, the other variations act as a vital safety net, dramatically improving the likelihood that we gather sufficient evidence to form a comprehensive answer. Let us look precisely at how RAG Fusion executes this wide net strategy. The process is broken down into 3 distinct phases. First is the generate phase. The large language model acts as a creative query generator, taking the user's single input and rewriting it into multiple variations, perhaps 4 or 5 different interpretations, each approaching the core question from a slightly different angle. Second is the retrieve phase. Crucially, these new query variations are executed simultaneously, in parallel, against the vector database. Instead of relying on one search result, we are now gathering relevant documents based on 5 separate, optimized searches. Third, and finally, we fuse the results. If a document is highly ranked in 3 different searches, it is likely extremely relevant, even if it wasn't the top result in any single search. To formalize this judgment, we use reciprocal rank fusion, or RRF. RRF is an algorithm that pools the results from all parallel searches and re-ranks them, elevating documents that consistently appear highly across the various query perspectives. The output is a single, highly refined set of fused, relevant results, ready for the LLM to synthesize into the final answer. While RAG Fusion excels at widening the search for a single step, the investigator soon encounters a challenge that requires sequential reasoning. We call this crossing the river of knowledge. This happens when the answer is not in one document, but is spread across a chain of them, requiring multiple inferences. This is the disparate information problem. Naive RAG, even with RAG Fusion, cannot cross this gap in a single, static search. Consider our challenge query. Who is the CEO of the company that acquired Slack? There is no single document that directly links Slack to Mark Benioff. A search for CEO of company that acquired Slack will likely fail or return irrelevant results because the system needs 2 distinct facts. First, identifying the acquirer, which is Salesforce, and second, identifying the CEO of Salesforce. To solve this, the investigator needs a new capability: the ability to execute multiple, dependent retrieval steps. This is the foundation of multi-hop RAG. Multi-hop RAG transforms the LLM into a sophisticated detective, following a trail of clues until the final answer is revealed. The key differentiator here is that the LLM is not just generating the final answer. It is generating the retrieval queries themselves, dynamically, based on what it just learned. Let us walk through the process using our Slack example. We begin with Hop 1. The LLM takes the original complex query and deduces the necessary first step, generating the subquery, who acquired Slack? The system executes this search and retrieves document A, which clearly states that Salesforce acquired Slack. Next is the crucial reasoning step. The LLM internalizes this new fact. It now knows the acquirer is Salesforce. This newly acquired fact then informs Hop 2. The LLM generates a brand new query based on its internal state. Who is the CEO of Salesforce? The system executes this second search and retrieves document B, which identifies Mark Benioff. Finally, we reach synthesis. The LLM combines the insights gained from both Hop 1 and Hop 2, linking the chain of facts, Slack acquired by Salesforce, Salesforce led by Mark Benioff, to form the coherent, grounded final answer. This iterative, looping mechanism allows the system to bridge wide informational gaps that were previously impossible to cross. Until now, both naive RAG and multi-hop RAG have suffered from a critical flaw: amnesia. Every query is treated as a completely fresh start, entirely disconnected from the previous conversation turn. This means the system has zero memory. This failure breaks the conversational flow and, maddeningly for the user, forces them to constantly repeat the context. Look at the example shown here, the broken conversation. The user asks, "Tell me about the Apollo 11 mission," and the system correctly responds with a fact. Immediately after, the user asks the simple follow-up question, "Who was the commander?" Because query 2 is treated in isolation, the system loses the context of Apollo 11 and can only respond with a confused, "I'm sorry, who is the commander referring to?" The system failed to forge the connection between the current question and the preceding topic. To be a truly effective investigator, our system needs to recall the past. It needs the third power: conversational memory. The solution to defeating amnesia and unlocking true conversational RAG is to fix the user's query before it ever hits the vector database. We introduce the stand-alone query generator, which is an LLM specifically tasked with this crucial preparatory step. This generator takes two inputs: the user's current query, which is often terse or contextually dependent, and the chat history, which contains the essential contextual facts from previous turns. The generator acts like a blacksmith, forging a key from the materials of the past. It rewrites the ambiguous follow-up question into a fully self-contained or standalone query. In our example, the input was the ambiguous "who was the commander?" Combined with the history Apollo 11, the LLM rewrites this into the crystal clear, context-rich query: who was the commander of the Apollo 11 mission? This standalone question is now robust enough to successfully retrieve the necessary document from the vector database, effectively unlocking the answer. Conversational memory ensures that the system is not merely retrieving information, but is participating in a fluid, continuous dialogue. We have successfully evolved from a simple lookup system into a complex cognitive engine, giving our investigator powerful new abilities. But these new capabilities come at a price, a fundamental trade-off defined by latency and cost. Every layer of advanced reasoning, every loop, every branch we introduce, requires more LLM calls and more retrieval steps. Intelligence is a deliberate trade-off. Consider the difference in resource use. Naive RAG is the most efficient, requiring just one LLM call to generate the answer. RAG fusion, which brainstorms multiple queries, dramatically increases the retrieval workload, needing one generation call plus potentially 5 or more parallel retrieval calls. Multi-hop RAG is even more computationally intensive, requiring 2 or more sequential generation calls to deduce the next step, plus 2 or more retrieval calls to gather the chained facts. The architect's choice is paramount here. As the system designer, you must strategically decide if the complexity of the user's question justifies this rising cost. We are literally trading milliseconds of latency and dollars of compute for intelligence, resilience, and superior synthesis capability. This diagram captures the hero's evolution, the fundamental shift from the naive RAG clerk to the advanced RAG investigator. The clerk was limited by a simple, linear pipeline. When faced with the unanswerable question, a query demanding synthesis, the linear path failed. The investigator overcomes this failure by adding complexity and cognitive functions. First, we introduce the prism of perspectives, or RAG fusion, which adds parallel branches, transforming a single search into a wide net to ensure robust retrieval. Second, we added the iterative journey, or multi-hop RAG, which introduces reasoning loops, allowing the LLM to string together clues and cross the river of disparate knowledge. Third, we integrated the stream of time, or conversational memory, which allows the system to recall context and maintain a seamless dialogue, forging keys from past interactions. Our system has fundamentally changed its nature. It is no longer a rigid, linear tool. It is a dynamic, intelligent framework with branches, loops, and memory, capable of solving entire classes of problems that were previously impossible for RAG systems. The evolution does not stop at the investigator. The final stage in this journey represents a paradigm shift. The investigator becomes the architect. We move beyond merely retrieving information to orchestrating entire investigative workflows. This is the expansive and powerful realm of agentic RAG. In all previous RAG systems, the underlying retrieval mechanism was fixed. The system knew it had to do RAG fusion or multi-hop RAG based on a predefined pipeline. In agentic RAG, the large language model itself is the core reasoning engine that doesn't just find clues, but dynamically decides the entire flow of the investigation on its own. The agent is the ultimate orchestrator. It decides which path to take, when to use a tool, when to verify a fact, running code for calculations, querying structured databases, or specifically calling external APIs for real-time data, all in an effort to construct the most accurate, grounded answer possible. The architect operates across new dimensions of knowledge, two of which represent the bleeding edge of RAG development. On the left, we have agentic RAG, which we call the self-directing mind. Here, the LLM acts as a high-level reasoning engine, choosing a sequence of actions rather than following a fixed pipeline. When the query comes in, the LLM decides, does this require running code for a complex calculation? Should I retrieve specific facts from a structured query database? Or is a standard search across the vector store sufficient? The LLM is the brain at every decision point, dynamically planning a complex path tailored precisely to the user's question, resulting in a robust, multimodal final answer. On the right, we explore structured graph RAG, or the constellation of facts. While standard RAG treats documents as flat chunks of text, graph RAG recognizes that knowledge often lies in the relationships between data points. Imagine a dense map where nodes are entities like people, organizations, or concepts, and the lines between them are relationships like employed by or acquired. GraphRag leverages vector embeddings, but specifically focuses on traversing this predefined map of knowledge. This is invaluable for superior logical queries, such as list all the suppliers of the organization that won the project start event. By traversing these explicit relationships, GraphRag can answer complex relational questions with precision and speed that linear document retrieval simply cannot match. Both agentic and GraphRag move us firmly into the next level of knowledge architecture. Let us consolidate our findings in the Investigator's notebook, reviewing the key takeaways from our quest. First, remember the baseline. Naive RAG is purely a one-to-one lookup mechanism. It is incredibly fast, highly efficient, and serves well for direct questions, but it is fundamentally brittle. It fails decisively when a query requires context, demands complex synthesis, or when the user's phrasing is ambiguous. Second, we learned that advanced RAG introduces critical complexity through loops and branches. Techniques like RAG fusion widen the search, making the retrieval process far more robust and resilient against poorly phrased queries. Multi-hop RAG deepens the search, allowing the system to reason sequentially across disparate documents. These advanced methods build systems that can successfully solve complex, multi-part queries that were previously impossible. Third, and perhaps most crucial for the architect, intelligence is a deliberate trade-off. Every layer of complexity we add to gain intelligence, whether it is an extra LLM call for conversational memory or multiple parallel retrieval steps for RAG fusion, adds latency and cost. The architect's role is to strategically balance performance metrics with the required cognitive capability for the task at hand. Do not over-engineer. Choose the complexity that justifies the intelligence gain. We conclude our quest with this powerful realization. The evolution from a simple, literal-minded clerk to an intelligent, sophisticated investigator is not just a technological upgrade. It is a fundamental shift in design philosophy. We must move beyond thinking in terms of simple, linear retrieval pipelines. To build truly intelligent RAG systems, we must architect frameworks that inherently possess the cognitive abilities we need. The ability to brainstorm multiple possibilities, the power to reason iteratively across chained facts, and the capacity to remember the context of an ongoing conversation. The next level of knowledge is not simply waiting in the database to be retrieved by a single, perfect query. It must be actively constructed. It must be synthesized. It must be reasoned. You now hold the blueprints for these advanced RAG techniques. You are the architect, ready to design the next generation of knowledge systems that are resilient, intelligent, and capable of solving the complex queries of the modern world. Thank you.